The addition of water hydration for alkynes is also similar to what you have seen in alkenes. So here's an example. So again, suppose we have this starting material, our alkyne H2O, H2SO4, or once again, this can be also summarized or can be written as simply H3O plus. Then your product in this case would be let me make this clear. Your product would be a ketone. Product would be a ketone. Now, let's look at the mechanism, because you actually end up making something quite interesting in this reaction. So the mechanism starts this way. You have hydronium, protons are electron poor, electron rich, protonates, so you have your alkyne turning into what we call a vinyl. This is a vinyl carbocation or cation. So once again, this H right here is that one right there. So obviously you have now water in solution, and water will be attracted to the carbocation. So this will result in formation of this intermediate. Now, of course, water does not like to remain as a group like that, so we have to remove one of the H's. So here's another water molecule that will take care of that. So that should become to you as really intuitive to you that oxygen with 3 bonds, you have to remove one of the H's. So fantastic. So this leads to the alcohol being added right there. Now we have, since we deprotonated the water to make the alcohol here, so we're back with an acid, which again, the double bond is attracted to. Right there. No double bond. Right there. Now, so we need more space here. Now, you might be tempted to say, okay, let me make the water molecule attack this carbocation, but you should be telling yourself not to do that, because that's not what the mechanism is telling us. So the mechanism is telling us that the product would be a ketone. There is no other alcohol group attached. And the reason why is because what is happening here is that this engages in the following manner, right? So what happens is that these lone pairs right here on the oxygen, they form a double bond between the oxygen and the carbon where the carbocation is, leading to this. And this, if you notice, offsets the deficiency in the octet here, because that's what the carbocation is. So then the water molecule, what it does is that the following. The water molecule actually acts as a base where it deprotonates this H right there, forming the ketone. There's no double bond here. My apologies. Let's see. So nothing happened here. I'm just rewriting it as this way. So that would be your product, is you're forming a ketone right here. Now, the reason why is now you end up with an acid. The reason why is because anytime you start with acid as a catalyst, you have to end up with an acid. And that's what we ended up with here. If we didn't do this step, then we would end up with water. And that's not what happens with catalysis. Catalysis is the process of using the catalyst to speed up the reaction, but the catalyst is not used up. You still get it out. It does a part where it speeds up the reaction rate, lowers the activation energy, but it does not become part of the starting material to make the product. So it does not play a role in changing it. That's what I'm trying to tell you here. There's one thing, since we're on this topic here, is that the carbonyl compounds with alpha hydrogens are in equilibrium with vinylic alcohol isomers called enols. So meaning that while you did make a ketone, this is a ketone, you can also have the enol version. An enol is, obviously, you have an alkene, that's what the en means, and the ol from the alcohol. So those, okay, are in equilibrium. However, this is in, the equilibrium is very, very, very tiny. Okay, the equilibrium is very, very tiny. Tiny amount. So what you form most of the time is the ketone. However, nonetheless, this process is called tautomerization. It's the conversion of an enol to a ketone by protonation at the carbon atom of the double bond and deprotonation at the oxygen atom, meaning that if you If you protonate this O right there, let me delete this circle. If you protonate this, then the oxygen can't have that many bonds. It's going to shift, create a double bond there, and that explains why the H there. So if we draw the H's here, you have 3 H's. Here you have 2 H's. So that explains how those H's are distributed, again, between these two, what we call tautomers. That's the process, is you have ketone and enol, but this is your major product. It's in equilibrium. The ketone. Most carbonyl compounds are considerably more stable than their enols. When an enol is formed in the reaction, it will automatically convert to its keto form in the presence of a trace acid or base, like as you see here, acid or base. So, should you draw, you might be asking, should I draw the ketone and the enol as a product? No, you should draw the ketone only product. However, if I ask you a question about on explanation, then you should be able to provide the enol form. The enol form should be provided. Terminal alkynes are less reactive. As you see here, this is a terminal alkyne and require the use of an additional catalyst. And this is your additional catalyst. It's a mercury-based catalyst. And if you see that, then that's going to give you a ketone. So you need this for terminal alkynes. You need the HgSO4. You don't need it for internal alkynes. The product is always a ketone except when acetylene, in this case, of course, you have acetylene. And if you notice, okay, you say, okay, what is this going to form? Well, you can't have a ketone here. You will have an aldehyde. So acetylene is the smallest alkyne. You will form an aldehyde. And of course, if you have an unsymmetrical terminal alkyne, it will give you a mixture of products, meaning you might have the double bond there or there. And it's hard to, let me draw this carefully. It's hard to separate them actually. So that's why it may not be a useful reaction. So that's 1 plus and that's 2. So be able to draw both of these. Now, lastly, is that if you have a terminal alkyne, if you use the mercury-based catalyst, like we said here, you will produce the ketone. So With this one, it's going to go there. However, as you saw with hydroboration, you will actually form the aldehyde. So it's the, in a sense, the anti-Markovnikov. So you will have right there. So be aware of the differences between these two reactions.